Imagine for a moment that everything you know, every star, every planet, every atom in your body, represents just a tiny fraction of an infinitely larger reality. That there are trillions of parallel universes where different versions of you made different choices, where the laws of physics work in completely different ways, where the very structure of reality follows rules that challenge our understanding. This isn't science fiction. It's a real possibility that emerges from the most advanced theories of modern physics. Welcome to the world of the multiverse, an idea as revolutionary as it is controversial, one that divides the scientific community between those who see it as the key to the cosmos's greatest mysteries and others who consider it pseudoscience disguised as serious physics. Today, we're going to dive deep into this fascinating debate. We'll discover how respected theories like eternal inflation and string theory naturally predict the existence of multiple realities. We'll explore why our universe seems so perfectly fine-tuned for life, a cosmic coincidence, or evidence that there are countless other universes where things went wrong. If you're ready to question the very nature of reality and find out whether we live in just one among infinite possible worlds, then hit that subscribe button right now, because some truths are too big to fit in just one universe. And today, you're going to discover why. Types of multiverse and their origins. Before we judge whether the multiverse is legitimate science or unbridled speculation, we need to understand exactly what we're talking about. And here lies the first problem. There are not just one, but several types of multiverse, each emerging from different and well-established theories in physics. Let's start with the basics. When we say universe, we traditionally mean the totality of existence. But in modern physics, universe usually refers to this specific continuous spacetime that traces back to our particular Big Bang. It's as if each universe were a giant bubble of reality, potentially surrounded by, well, other bubbles. The first type is the quilted multiverse. Imagine a space-time so vast that in extremely distant regions, the very laws of physics begin to change. Like a quilt made from different patches, each region would operate under slightly different rules. It might sound weird, but there's nothing in the known laws of physics that prevents this. Then we have the eternal inflation multiverse, and this is where things truly get spectacular. The theory of cosmic inflation, which beautifully explains many features of our observable universe, suggests that the greater spacetime is expanding much more rapidly than our local universe. Occasionally, bubbles of gentler expansion form, each becoming a complete universe like our own. It's like soap foam on a cosmic scale, where each bubble is an entire reality. String theory takes this even further. It proposes that all matter and energy are fundamentally composed of tiny vibrating strings in compactified extra dimensions. The geometry of these extra dimensions, called Kalabi-Yau manifolds, determines which particles exist and how forces work. The problem is, there are at least 10 to the 500th power different possible configurations. Each would create a universe with completely different physics. To put this number in perspective, if you counted one configuration per second from the Big Bang until today, you still wouldn't have even scratched the surface of this astronomical number. This is where we encounter the string landscape, a conceptual vastness of possible universes that may or may not exist out there. But why our specific reality? Why does our universe have exactly the properties needed to form stars, planets, and life? The answer might be surprisingly simple, and at the same time, deeply unsettling. And that's exactly what we'll discover in the next chapter, when we explore the Anthropic Principle, an idea that could completely change your perspective on our place in the cosmos.
The Anthropic Principle and universal fine-tuning. Here's a fact that should keep us awake at night. Our universe appears to have been fine-tuned with surgical precision to allow life to exist. Slightly change the mass of the Higgs boson and fundamental particles wouldn't form correctly. Adjust dark energy's strength a bit, and the universe would either collapse in on itself or expand so rapidly the galaxies would never form. Tweak the dimensions of space-time, and physics becomes impossible for the complexity we see. These aren't rough adjustments. We're talking about precision that would make a Swiss watchmaker weep with envy. The probability that all these parameters just happen to randomly fall into the correct values is so small, it's almost mathematically zero. So how do we explain this extraordinary cosmic coincidence? This is where the Anthropic Principle comes in, one of the most elegant and controversial in modern physics. In its most reasonable form, it argues that we shouldn't be surprised to find ourselves in an unusual part of the universe, or multiverse, because we ourselves are unusual. Think about it this way. You don't get surprised when you wake up every morning on a planet with breathable atmosphere, suitable temperature, and liquid water, right? Even though habitable planets occupy an infinitesimal fraction of the universe's volume, you're on one because, well, you have to be somewhere where you can be. It's an obvious selection bias. The Anthropic Principle extends this logic to the multiverse. If there are countless universes with all possible combinations of physical laws, then naturally we find ourselves in one of the very few where life is possible. Not because we were specially chosen or because there's some intelligent design, but simply because it's the only type of universe where observers like us can exist to ask this question. But some physicists take this much further. They argue that our universe's apparent fine-tuning is actually evidence for the multiverse's existence. Steven Weinberg, a Nobel laureate, showed that anthropic arguments made a pretty accurate prediction for dark energy's value, assuming our universe should have the most likely value that could still permit our existence. It's a complete flip of logic. Instead of using the multiverse to explain fine-tuning, we use fine-tuning as evidence for the multiverse. It's like finding a specific playing card on the table and concluding there must be thousands of decks scattered around, because it would be impossible to find that specific card if there were only one deck. But here's the problem. This line of reasoning takes us into dangerous philosophical territory. If anything is possible somewhere in the multiverse, do we still have real science? Or have we just created the ultimate excuse for not having to explain things? And it's exactly this tension between explanation and speculation, between robust science and disguised philosophy, that's at the heart of the biggest controversy about the multiverse. A controversy that involves nothing less than the very definition of what constitutes good science.
Occam's razor and the scientific controversy. Never postulate pluralities without necessity. These words from William of Occam, written over 700 years ago, are at the center of one of modern physics's fiercest intellectual battles. The multiverse represents the biggest plurality conceivable. Trillions, perhaps infinite universes. Does this fundamentally violate the principle of scientific parsimony? Multiverse critics are relentless. How can we call something science when it postulates the existence of realities we can never directly observe? It's like creating a theory that explains everything by explaining nothing. If anything is possible somewhere in the multiverse, then we completely lose the predictive power that makes science special. And there's the falsifiability problem. Karl Popper argued that a theory is only scientific if it can potentially be refuted by experiments. How do you test the existence of universes beyond our observable horizon? How do you falsify string theory when it predicts 10 to the 500 different universes, most of which would be impossible to distinguish from others? But there's a powerful defense against these criticisms, and it starts with a more refined understanding of Occam's razor. The principle doesn't tell us to minimize the number of things that exist. It tells us to minimize the number of assumptions we make in our theories. There's a crucial difference there. When eternal inflation theory naturally predicts a multiverse, that multiverse isn't an additional assumption. It's an inevitable consequence of the theory. It's like discovering that the equation describing waves in water also applies to sound in air. You're not unnecessarily multiplying entities. You're discovering that your theory has broader implications than you initially thought. The history of science is filled with moments when we accepted realities much larger than our intuition suggested. The ancients rejected the idea that Earth orbits the sun because it would imply that stars are absurdly distant to explain why we don't see parallax. They were wrong. Stars really are that distant. In the Great Debate of 1920, Harlow Shapley argued against the idea that galaxies exist beyond the Milky Way because it would make the universe uncomfortably large. Today, we calmly accept an observable universe 93 billion light-years in diameter, and a larger universe hundreds of times bigger, possibly infinite. The pattern is clear. As our measured boundary of the universe expands, so does our acceptance of new, increasingly preposterous sizes. Why stop now? As for testability, this is more subtle than it seems. While we can't travel to other universes, we can test the theories that predict them. String theory makes specific predictions about the distribution of universe properties in the landscape. Anthropic arguments can predict what kind of universe we should expect to observe if we're really the product of selection in the multiverse. Steven Weinberg used anthropic reasoning to predict dark energy's value with stunning accuracy decades before its experimental discovery. If that's not testable science, then what is?
But here's the crucial point that separates good science from speculation. Everything depends on how you approach the multiverse. If you propose it simply as a general answer to fine-tuning without a concrete and testable mechanism, then yes, you're doing bad science. But if it emerges naturally from well-founded theories that make other verifiable predictions, then it can be legitimate science. And this brings us to the final question. In a universe where even reality itself might be multiple, how do we distinguish between scientific possibility and philosophical fantasy? The future of reality. We've reached the end of our journey through possible worlds, and the question remains: is the multiverse brilliant science or disguised speculation? The answer, like many things in modern physics, isn't black and white. but rather a fascinating shade of gray. What we've learned today is that the multiverse isn't a single idea, but a set of different possibilities emerging from respected theories in physics. When eternal inflation naturally produces bubble universes, when string theory mathematically requires a vast landscape of possible realities, when our universe's very fine-tuning suggests there must be others where things went wrong, we're no longer in the realm of pure speculation. The fundamental criterion is this: if a theory was developed to solve specific physics problems and happens to predict a multiverse as a byproduct, then that multiverse deserves serious scientific consideration. If, on the other hand, the multiverse is invoked only as a convenient answer to difficult questions without testable mechanisms or verifiable implications, then we really are in the territory of bad science. The truth is that our intuitions about what constitutes a reasonable reality have consistently been challenged by science. From the heliocentric system to the cosmos' vastness, from quantum mechanics to relativity, reality has repeatedly proven stranger and grander than we ever imagined. Maybe the multiverse is just the next step in this journey of discovery. Maybe it's the key to understanding why we exist in a universe so perfectly calibrated for life. Or maybe it's a conceptual dead end that diverts us from the true fundamental questions. What's certain is this: if the multiverse exists, then every choice you didn't make, every path you didn't follow, every possibility that didn't materialize in your life all exists somewhere, in some parallel reality. There's a version of you that made different decisions, who lives a completely different life, who might be watching a different version of this video in a universe where the laws of physics are slightly different. It's an idea that's both humbling and liberating. Humbling because it suggests our reality might just be one among infinite possibilities. Liberating because it means the cosmos is much richer, more diverse, more full of potential than we ever dreamed. Science continues its relentless march toward truth, and if that truth includes multiple realities, then so be it. After all, if there's one lesson physics has taught us repeatedly, it's that reality rarely cares about our preferences for how it should be.
The multiverse might exist. And if something that exists can be bad science, then maybe it's time to expand our definition of what constitutes good science. Because in an infinitely creative cosmos, even our ideas about science might need to evolve. And you, after everything we've discussed today, do you think we live in a unique and special universe? Or are we just one reality among infinite others? The answer might be closer than we think, or farther than we could ever imagine.